Intermolecular forces. You will commonly see this shortened into IMFs. When we talk IMFs, one of the things you want to keep in mind is there is a difference between intra and inter, and this goes back to basic English. Intra is between, intra is within, inter is between. Intramolecular attractions are the common bonds where you should already be familiar with: covalent, ionic, metallic. So that's what's happening here. That's what's in between the two atoms. Inter is what's going on between molecules. The reason we care so much about intermolecular forces is their impact upon observable macroscopic properties. So we often talk about the role of intermolecular forces when we deal with physical properties. This is why when you compare real gases to ideal gases, there are some differences in behavior, because remember that when we dealt with pressure, volume, amount of gas, and temperature, those were all physical properties. When we talked about how 1 mole of gas occupies exactly 22.4 liters at STP, that was a physical property of the gas. This is why intermolecular forces are so important when we deal with gases, liquids, solids, etc. And this is because they impact boiling and melting points, what we want to call vapor pressure, and viscosities, which we'll be dealing with in the next section. Now altogether, when we talk intermolecular forces, this is what's termed van der Waals forces. So really, the three forces we're going to deal with are London dispersion, dipole-dipole, and hydrogen bonding. Together, those are all known as van der Waals forces. So one reminder too, remember that hydrogen bonding is a special form of dipole-dipole interactions. So let's start with London dispersion. When you look at London dispersion, this is basically, when we go through the next few slides, this is in essence an explanation for figure 11.4. Ultimately, what is going on is we know that electrons are always moving. Because electrons are always moving, they have a tendency to repel each other, yes, but every now and then, because they're moving, they end up on one side. It's sort of like that freak thing when all of the planets line up in their orbits around the sun. When this happens, what's really cool about it is we see this induced dipole. So we have this ability to have one molecule end up with this imbalance, and as soon as it gets near another molecule, it causes the new molecule to create a dipole. We induce it in the neighbor. This is in essence at the heart of London dispersion forces or dispersion forces. Now, the reason we know that this has to happen is because nonpolar compounds or neutral atoms and molecules, they change. In other words, the fact that we can make nitrogen gas become a liquid, or helium gas become a liquid, or argon gas become a liquid implies that there is something going on. There is something that allows that to occur. Now, even though these exist in all molecules, larger molecules find it easier for this to occur. This is what's referred to as the polarizability. So that ability to induce a dipole in neighboring compounds. So the larger my atom, the more electrons are present. The more electrons are present, the easier it is to induce a dipole, to induce that imbalance of location. And this is in essence because molecular size and mass, they basically parallel each other. You can see this in figure 11.5, where it shows you that impact of the dispersion forces and the changes in the boiling point of both the halogens and the noble gases. So we have neon, argon, krypton, and xenon. And then you see exactly a similar trend with the noble gases, with the halogens. So notice how that temperature changes as you go down, where we have more and more electrons. And to reinforce the reason this is so significant here is because the only intermolecular force in these compounds is London dispersion. So that's the only IMF occurring in these compounds and in these atoms. Now the last influencer on London dispersion forces, we shall say, is the shape of the molecule. And this has to do with, in essence, what would be your surface area. More surface contact can occur with a straight molecule as opposed to this rounded molecule, and so that increase in surface contact increases the likelihood of greater London dispersion forces within the molecules. So if you have any kind of polarizability here, because they can come into contact with more and more, I have an easier chance of inducing polarizability here as opposed to the narrower surface area contact here. The next IMF is dipole-dipole interactions. The most important feature here is this idea of a permanent dipole. In other words, we have compounds that are polar. Remember from chemistry that a polar compound is simply an unequal sharing of electrons within a covalent bond. And this has to do with the electronegative differences between the nuclei of the atoms involved. Now, what's significant in terms of what you're seeing in this diagram is when you look at the left versus the right, notice that the left one is solid, okay, this is solid, and this one is liquid. And this is kind of obvious by the interactions and the set location because of that interaction. So we get a very solid, very strong crystal lattice association. This is similar to what you see with water. This is why ice is actually less dense than water, is because the water has to organize itself so that all of the positive attractive interactions are set so that oxygen's exactly by two hydrogens and two hydrogens are exactly by different oxygens, and so it gives it that expanded crystalline structure. Now we see both repulsive and attractive forces when it's in the liquid, but the attractive forces are still greater in number than the repulsive forces, and this is why when we see dipole-dipole interactions we see an impact on the boiling point of many liquids. And in fact, that boiling point, you see that increase as you have a greater polarity, as you have that increased attractiveness. And so because of that attraction, they tend not to leave the liquid to become a gas even with heat. Now, remember how this contrasts with the London dispersion forces, because the London dispersion forces, they weren't permanent, they were instantaneous. Oops, let's redo that. They're instantaneous, meaning they form in an instant. So it's due to the movement of the electrons, not the nature of the bond within the molecules. So when we talk instantaneous, we're dealing with movement of electrons, randomly occurs. When we deal with the permanent dipole itself is a product of the intramolecular bond, the polar covalent bond, impacting the intermolecular forces between the molecules. And again, this impact is most commonly seen in terms of boiling point and melting points. Now, when we compare the impacts, in other words, if we talk the strength of the force, dipole-dipole is generally stronger than London dispersion if both are present. And the larger the molecule, as mentioned previously, the more likely the London dispersion forces will have an impact. Now, where we see this trend is obviously when we compare compounds within a group. So here you can see we have CH4, which is methane, SiH4, GEH4, etc. And so we can see that trend. You can see that trend here with the hydrogen iodide, hydrogen bromide, hydrogen chloride, etc. You can see the trend that we would expect to follow. Now, what's significant, however, is that these three, water, hydrogen fluoride, and ammonia, do something more. In other words, by nature of this pattern, it looks like they should be down here just above CH4. Instead, they're way up here, and in fact, you see this dip in boiling point before it rises again, and even as it rises and we see more and more London dispersion forces, it doesn't necessarily match where we started with the smallest ones. So we have a particular type of intermolecular force going on here, and that's the hydrogen bonding. Now, what's significant again is that we have a very polar bond. So we have a polar intramolecular force, and so hydrogen is in essence without electrons most of the time, and it becomes attracted to these lone pairs of electrons that are not used in any bond. And note that that unpaired use of electrons has to be on a different molecule, hence intermolecular. Now, it becomes significant because hydrogen bonding is what explains that unusual jump that we observed here with water, hydrogen fluoride, and ammonia. And so that jump is what accounts for this. Now, notice that we have hydrogen being attracted to a very electronegative atom. Okay, these are some of our most electronegative atoms on the periodic table. So what you have to remember is, since our hydrogen nucleus is in essence exposed, hydrogen is considered electron poor. All we have is basically an exposed proton. So that means our really, really small hydrogen atom can get really, really close to that high electronegative atom. And therefore, because it's literally closer, we have a strong interaction between the two molecules. And that's why hydrogen bonding is more effective, shall we say, than just dipole-dipole in terms of these small atoms and their boiling points. Now, this also becomes significant when we talk solvation. So remember in the previous section when we talked about the interaction of and that solvation, that dissolving of an ionic solid in a polar solution, in this case water. You see that interaction because of these negative charges and these positive ions or negative ions. That interaction is strong enough that literally it can pull it out of its ionic compound, out of that crystal lattice, and dissolve. And this is why almost all ionic compounds do dissolve. Now, the figure, the flowchart, is really nice for determining which intermolecular force is occurring. I would definitely copy this into your notes.